Hi, I'm Bob Lessick with the Center for Biotechnology Education at Johns Hopkins, and I'm going to walk you through a problem involving weighted coins. Hopefully, this will show how that's relevant to the binomial equation and help you get started with problem solving. First, we want to explain the major components of the binomial equation. Also, be able to do the calculation of the number of possible ways to get x successes out of n events. That sounds like a mess. Let me put real numbers in there. How many ways are there to get 3 successes out of 9 trials? How does success probability fit into the equation, and how does failure probability fit into the equation? Finally, be prepared to discuss issues and complications that might arise. Starting with some basics about the binomial distribution. By definition, events are independent, and we can also take advantage of mutually exclusive events being additive. With independent events, how do we calculate the intersection of events? Well, if they are independent, we can multiply. Those independent events and mutually exclusive events set up the math in the binomial equation, as we will see shortly. Okay, so we have a slightly unfair coin. The probability of heads is 0.501, and the probability of tails is the complement of that, so 0.499. Basically, it's only slightly unfair. Let's flip it 4 times. What is the probability of getting exactly 3 heads out of 4 flips? Well, how many ways are there to get 3 heads out of 4 flips? Fortunately, it's easy in this case. There are only 4 ways it can work, because tails can only come up once if you have exactly 3 heads out of 4. HHHT means the 4th one was tails. HHTH means heads, heads, tails, heads, so the 3rd one was tails. HTHH is tails on number 2, and THHH represents tails, then 3 heads. There are only 4 ways. With these small numbers, it was easy to solve. It would be a lot harder to get the number of ways to get 3 heads on 10 flips. Let's look at each of the 4 outcomes: HHHT, HHTH, HTHH, and THHH. Well, since they are independent events, we can multiply probabilities. So, PHHHT is equal to PH times PH times PH times PT. So that's 0.501 times 0.501 times 0.501 times 0.499. Or it's 0.501 to the 3rd times 0.499 to the 1st. So look at it carefully. The success probability raised to the power of the number of successes times the failure probability to the power of the number of failures. The other 3 outcomes all have the same probability, all 0.501 to the 3rd times 0.499 to the 1st. Now we can add the probabilities. Why can we simply add? Well, HHHT, HHTH, HTHH, and THHH are all mutually exclusive, and we can add probabilities of mutually exclusive events. We wind up with 4 times 0.501 to the 3rd times 0.499 to the 1st. Breaking it down, that's the number of combinations, 4, times the success probability raised to the number of successes, 0.501 to the 3rd, times the failure probability raised to the number of failures, 0.499 to the 1st. So to summarize, we see combinations, ways to get 3 heads, then success probability to the 3rd because 3 successes, and then failure probability to the 1st because 1 failure. Now, it was easy for us to see that there were 4 ways to get exactly 3 out of 4 heads. Other times, it's harder. Here is the equation. In our case, n was 4 and x was 3, so 3 out of 4 heads. So, the number of combinations is, in the numerator, 4 factorial, divided by the denominator, which is 3 factorial times 1 factorial, which is 4. If it ever comes up, note that 0 factorial, by definition, is 1. Then here is the general form of the binomial equation for x successes out of n trials. Breaking it down, it's the number of combinations, that's the fraction with the factorials, times success probability to the number of successes, so p to the x, times failure probability to the number of failures, or 1 minus p to the n minus x. Some questions to ponder. A player is successful 1 out of 3 times on average and has 4 trials. What is the probability of at least one success? Why is that the case? What if there were 5 trials? What complications might arise? Statistics books are full of baseball, and it probably drives some people crazy. Why baseball? Is there a reason why statisticians love baseball? In any case, think of other examples outside of baseball and how you could solve binomial problems. Good luck.